But like you said in class a while ago, was that the problem now will be seeing a question and figuring out which equations I need
Yeah.
to use. So and then I know you mentioned there like keywords to look for, like if it ever says something about like a reaction happening over water, then I'll need to find the vapor pressure of water.
Mm-hmm.
Versus like if I see a really huge or small volume or temperature, that I know I'll probably need to use the like the real gas law, stuff like that.
Yeah.
Um, for the homework, some of the confusing ones I saw were the yeah, I guess I'm trying to remember some of the confusing ones from the homework we just did.
Logging into it as well. I'm going to make a list. Hi, Tatiana. Thanks for joining us. Well, we could definitely go over like a list of red flags and what that would connect to for an equation.
Right. I think I think the confusing equations are when we have to do gas stoichiometry. So we have to use the molar coefficient, and when it's appropriate to use PV equals nRT, and when we should use like P1 over V1, P1 V1 over T1 equals P1 V2 over V2 over T2, that kind of thing.
Mm-hmm. Okay. Tatiana, I'm gonna go over, this is a question about 161. I'm gonna go through it and then I'll go to you for the next one, okay?
Yeah, no worries.
Cool. Also, guys, if you're all right with it, I'm gonna record this so I can post it for other students. Is that all right?
It's okay with me.
Fine with me.
Awesome. Okay. So red flags for problems. So like the stoichiometry red flags are that you get limited information, right?
Mm-hmm.
And that there's usually a chemical equation given.
With coefficients.
Right. Or you have to balance it yourself, right? Mm-hmm. So in 121, someone would get that balanced. In 161, you might have to balance it yourself first.
Mm-hmm.
So with that, you might also see two pieces of information like mass or moles. And that's going to be the limiting reactant. Whenever the big thing, especially with the gas stoichiometry or the solution stoichiometry, is because those are both possible on this exam, is whenever you see you're given information about one or two molecules, and then you're asked to find out something about a molecule you have no information for. And that's the big, you have to use stoichiometry. And using stoichiometry just means there's a mole-to-mole conversion that you have to do to go from that one that you know about to the one that you're being asked about.
Right.
And then from there, if it's asking about pressure or volume, then you use the ideal gas law to get to it. If it's asking about mass, you use the molar mass to get to it. So that's still a lot of navigating.
Mm-hmm.
But that's the best way to tell that's what to do.
When do you use the molar ratio? You know how there was an equation that was like pressure of A over pressure total is equivalent to the moles of A over total moles, gives you X A, gives you the molar ratio. When am I using that equation? When am I using that variable?
You're using mole ratios for knowing about gas mixtures or part of a gas mixture. So
could we do a practice problem with that?
So a gas mixture is going to be one of your big hints that you might need to use it, and it's going to be something that is asking or giving information about moles and pressure, and that's it. It won't be necessarily volume and temperature involved at all. So you'll just see moles and pressure.
Yeah.
So I would say that you had a gas mixture. All right, now I'm going to make something up off the top of my head, and that's always a challenge. So if you know that you have a mixture of gases that's like 60, so like that, 60.6 atmospheres of oxygen and 0.4 atmospheres of nitrogen. Sorry, I'm struggling with creativity. You would be able to, with this, get a, so you have 1 atmosphere total. You could create a mole ratio for oxygen that was 0.6 divided by 1. So you'd have a mole ratio of 0.6. I know this is kind of simplistic. And so then if you knew the pressure of the total mixture, you could then find the pressure of the oxygen. Or sorry, the number of moles of the total. So if we know there's 10 total moles, how much O2 is there? We would just multiply the mole ratio times the number of moles.
And you might have an equation where we have to sort of combine this with maybe, the ideal gas law.
Yeah, this one, we'll use it since it's just really a concentration thing. It might be isolated on its own. I'll more likely combine the ideal gas law with vapor pressure problems with gas mixture, since we spent a lot of time on those. So these types of problems will probably mostly just be giving you information about moles and pressure, or asking about one of those two.
Yeah.
So for ideal versus combined, this one, if moles is mentioned at all, then you use the ideal gas law.
Oh, really?
Yeah. That simplifies it, right? If you're given either pressure, temperature, or volume changing, and so you have 2 values for one of those, that's when you use the combined gas law. Or if it doesn't mention moles. Unless it's talking about density, then that might be actually, never mind, misleading.
So then in that case, we'd use the combined gas law, and we would use probably what, the second of the 2 values given, or the value that represents like the second half of the equation, the state.
Probably what you'll have is something changes, like let's say temperature changes, so you plug that in. They'll tell you something stays constant, like pressure, right? So you'll plug the same one in on both. You'll be given one of the volumes, and then you calculate the remainder.
Right.
Yeah.
I think I was trying to do that with gas mixtures, and they all canceled because nothing changed.
Right. So something has to change. So if something's changing, use combined. If moles are mentioned, use the ideal gas law. If it's just moles and pressure, you can get around the ideal gas law by using mole coefficients. Of course, you could probably calculate it with just 2 iterations of the ideal gas law too, if you get stuck.
Okay.
Yeah. I'm trying to think if there's other ones. And then if there's anything about density or molar mass, then you use that version that combines density, mass over volume, the ideal gas law, and the molar mass equation.
Pressure times molar mass equals density times gas constant times temperature.
Or if you're mean, you can never remember anything except like a few. Like I just always derive it every time because I can't keep this one in my head.
Pim dirt.
Good idea.
Okay.
Are there any others that are hard to tell when to use them?
Those were the tough ones for gas. I also am not totally comfortable with the kinetic energy equations and the average kinetic energy equations.
Right.
I think it's just I got to remember to like whenever I'm using that equation, I have to remember to convert it to kilograms per mole.
Well, so if you think about the example problems we did, right? We didn't spend a lot of time calculating average kinetic energy. Like I don't think we did that at all. What we focused on was looking at rate is equal to the square root of the molar mass in kilograms of the two, but flipped. So I would focus on this one, and this will be whenever we're talking about which gas is the fastest.
Right.
The conceptual understanding of the average kinetic energy is important, though. For a calculation problem, though, I wouldn't worry about plugging into the kinetic energy equations.
Are we gonna be doing much on like calories, kilojoules, kilocalories, kilowatt hours?
That was actually chapter 5, right?
Yeah.
So that's going to be on the next exam.
Cool. Okay, well, I feel pretty good about most of that stuff.
Good. Yeah, since it's just 4 and 9 and we kind of got behind and it's not much of 5, it'll be very math heavy, but it'll be okay. All right. Well, if that covers that, I'll switch and take a question from Tatiana, and then I can come back and do any homework problems that you said were tricky.
Oh, totally. Yeah, I'm sorry. Yeah.
Oh, no, don't apologize. I'm just going to flip back and forth when there's multiple people. Hey, Tatiana, what do you want to go over?
Hey, I just wanted to verify. So when we're having a stoichiometry problem and we're making all of our conversions and applying them, we're pretty much just using Avogadro's number when we don't have, let's say, like a molar mass for one of our numbers, correct?
You're not going to use Avogadro's number in a stoichiometry problem, probably.
In some of our homework problems, we've had to.
Oh, for a couple of them, they like tied at the end.
Yeah, to get it into mass from moles.
No, that's not Avogadro's number. So, well, if it's mass, then from moles, it's molar mass. Go over a specific homework problem if you want. But you're going to use Avogadro's number, the 6.02 times 10 to the 23rd. Whenever you're asked about or given the number of atoms or the number of molecules.
Yeah. I don't remember what exactly it was. It might have been like not the mass, but like we were doing like a molecule into moles or something, but like we didn't have there was like an unknown for one of our things or one of our compounds, and so we were having to use Avogadro.
Was it a homework problem? It's not ringing a bell, but I can look.
It was towards the end. It was like
the harder ones.
Yeah, none of them were given. It was like A and B, and if you had like X amount of grams of A or molecules of A or whatever, then what is all of this? And it made you answer a bunch of questions based off of just that.
Yeah, I found it. Yeah, and they did the variables instead of the chemicals. So how many molecules of substance B are produced when amount of grams of A reacts? And it gives you the molar mass. So in this case, what you're doing, you're right. So again, the key word there, though, is molecules, and that's when you use it.
You had to use it to get it from
Right. And so this is whenever you're going in between moles and molecules. And so what it's saying is like, we're going to give you grams. We want you to convert into moles.
Mm-hmm.
And then we want you to convert into moles of B. And instead of giving us the mass, because we're not going to give you the molar mass, we want to know the number of molecules that it actually is. And so that's when you would use the 6.02 times 10 to the 23rd molecules per mole. And so look for that language when you're doing or seeing problems, molecular atom, and that's when you know to use that. And whenever I see that in a problem, I usually just write it out right away underneath it because I know I'll probably have to use it.
Okay.
But on the exam, like homework problems can get harder. Like I'm not gonna, it's most likely for your exam that you will have a straight stoichiometry problem.
Okay.
Or a reactant problem, because that was the focus in our in-class problem solving and in the lectures.
All right, cool.
We have to say, yeah, this is important, but Anything else on stoichiometry though?
No, I got most of it. I just had like a killer migraine when I had to take my quiz, so it didn't show as much, but I, in general, actually understand it.
Excellent. That sucks. Next time you have a killer migraine when you have to take a quiz, let me know and you can just take it after you have the migraine.
I will keep that in mind. Thank you.
Cool. Any other questions or thoughts?
Not at the moment. No, thank you.
Cool. All right, Ben, let's switch back to you if you want to go over any other issues or homework questions.
I had a question about system versus surroundings.
Mm-hmm.
If you had if you have like, so sodium ions combining with chlorine ions to make sodium chloride, would the product sodium chloride, would that be a system or would that be part of the surroundings?
Oh, it would totally be part of the system.
Okay.
So the whole chemical reaction is going to be part of the system because the whole transformation process is what's going to give off or absorb heat from its surroundings. And so the surroundings will be anything that isn't part of the chemical equation.
Yeah, I just didn't know if like once sodium chloride was formed, then it's like inert and it's not doing anything anymore. Maybe then that is like part of the surroundings. I don't know. I just wanted to clarify.
So if you had something that was like you're doing the reaction in a buffer and the buffer's not participating in the reaction, or like there's something else in the solution other than water that's not participating in the reaction, then that would also be the surroundings. But anything that is a reactant or product will be the system.
Yeah. Okay, cool. I don't know if I have many more questions. I'm feeling pretty good, I guess. I'm wondering what when we're doing like vapor pressure of water, we want before we use PV equals nRT, we would need to subtract the pressure that water is giving off before using that in our equation. Would we ever? I mean, that's pretty easy. That's pretty straightforward.
Yeah, you just have to remember to do it.
Yeah.
So like on the problems with the vapor pressure, people either totally get it or they go away, sorry. Or they forget to do that piece of it. But that's usually it. That's the big mistake on that one.
And then we wouldn't really get a wildly different number, so to clue us into that.
Right. Like it will look reasonable either way.
Yeah. I don't know. I guess I'm feeling pretty good. What do you think? What do you think I should make sure I feel really comfortable with?
I am totally probably going to put a gas stoichiometry in there, or a solution stoichiometry combined with gas stoichiometry. So be prepared for that. It'll be the same format. Some of the the multiple choices typically come out of things that are preparatory work for the ACS exam. And some of the ones for this section are kind of like, the multiple choice will not be like easy. They'll be like calculations. So be prepared for that.
Okay.
And the short answer, just make sure you're ready to do the claim, evidence, reasoning. But if memory serves me correct, you were pretty familiar with that on the last one.
I feel pretty good about that, yeah.
Yeah. And so that'll probably be in a more conceptual question. Yeah, I don't know.
Okay, well, I appreciate the things we talked about, and I feel pretty good now.
I think it's good. I think you should go in feeling very confident.
Yeah. I think I will depart the meeting.
All right. Have a good rest of the day. If you think of anything else, drop me an email.
Will do. Thank you very much. See you later.
Bye.
So, you're essentially going. So you said with the multiple choice, they're going to be like multiple choice calculations.
That is for my 161 class.
Okay, cool. I was like, what?
So like the 161 versus 121, I'm also secretly preparing the class to take this standardized exam at the end of a 3-quarter series that covers the whole 3-quarter series, which is just like awful. So I put in these awful multiple choice questions that I don't put on your guys' exam.
I appreciate that and feel terrible for them.
Yeah, I know. So people like multiple choice questions though, and they totally rock them. I'm not that person, so I always feel super guilty about it. So
I think they have a benefit if the person hasn't prepared for the material because they have like a chance to like process of elimination it.
well, there's also an art to taking a multiple choice test, right? Like eliminating things quickly and like knowing which ones to do first and second. Like there's a whole strategy that some people are trained in and others aren't. And so, yeah, if you've got those skills, then you're like, sweet, bring on the multiple choice. I got this.
Yeah. I think it just eliminates a whole bunch of people in the test though and like doesn't end up reflecting their actual knowledge sometimes.
Yeah, I mean, you could say that it's not a very good assessment tool at all. And I would agree with you like 20 times over. Say that it has some real bias to it. Whatever. Honestly, all these written exams in a timed, stressful location do that. They're awful.
Yeah.
Yeah.
Fun.
Yeah, side rant. Your guys' exam will probably have, since it's got all this stoichiometry stuff and drawing in it, probably have not that many multiple choice. I think it's got just 2, maybe 3. And they're going to be some of the easier questions, I think. And then there's going to be like a lot of drawing and calculations on it.
Okay.
So expect that.
All right, cool.
Yeah.
All right. Well, I shall go study. Thank you for your help.
Yeah, if you think of anything else, hop back on or send me an email.
Yeah, I will do that. Thank you.
So, bye.
Bye.